Hello, everybody, and welcome to Las Vegas. I trust the conference is off to a great start for everybody. Maybe some of you were even at the Raiders versus Chiefs game this weekend. In any case, today, we're excited to discuss with you how we leveraged AI/ML not only to capture the sports complexities that are most interesting to NFL fans, but also what kind of engagement that drove and to what magnitude. I'm Elena Ehrlich. I'm a principal science manager. I've been with AWS some 6+ years. And in working with the NFL, our team developed some of the machine learning models that you're familiar with behind the next-gen stats metrics. Before we get started, I'd like to invite my colleague, Arti Sani, for her quick introduction.
Thank you, Elena. Hi, everyone. My name is Arti Sani. I'm a senior practice manager in AWS Professional Services, also known as PRO304. My team has been helping a number of media entertainment customers and sports customers, such as the NFL, to transform their business through innovation on AWS, using technologies such as GenAI, AI/ML, data analytics, and more. And it's now my honor to welcome Andrew from NFL Next Gen Stats team. Welcome, Andrew.
Thank you, Arti. And thank you, everyone, for being here. Good afternoon. My name is Andrew. I'm the Director of Engineering for NFL's Next Gen Stats. It's been so exciting and rewarding to see the engagement of fans and broadcasters evolve in recent years since Next Gen Stats, or NGS as we call it, began capturing the player tracking data and delivering insights into today's game. In my 8 years on the NGS team, our focus has always been, how do we maximize the value of the player tracking data? Well, it started with speed and distance, simple calculations based off of time series coordinate data. And this would give us things like, oh, he reached 22 miles an hour on this play. Or he had to run 60 yards just to gain 2. Now, since we also know who's on the field, we can capture things like offensive formation, so shotgun, is he under center, pistol, I form. We can also capture personnel packages, like 21 stands for two running backs, 1 tight end. And then we also know what happens in the play. So a running back rushes up the middle, or it's a catch outside the numbers. These were things that were typically done by an army of people watching every single play on game film. Not to mention, different teams would have different focuses based off of who their upcoming opponent was. Us being able to label this in real time on every single play was a huge win. And it represented a massive savings in time and effort on behalf of the teams. And yet, there was still this potential to make better sense of the data and potentially quantify the impact individual players might have. All tight ends can catch a ball. All tight ends can block. Why is it that Travis Kelce has an outsized impact and role on his team than the average tight end in the league? To convert this potential to real, actionable insights, the league partnered with AWS PRO304, whose consultancy of experts include Gen AI, ML, business, and technology. This is what we're going to be covering in today's session. I'm here to tell you about the NGS journey, our deadlines, our hurdles, the unquenchable thirst of our fans and our teams for more data. And while the NFL puts on some of the largest events in the world, every department at the NFL runs very lean. Does that sound familiar? How about this? My engineering team of 4 are responsible for everything from building infrastructure, so we're writing Terraform and CloudFormation scripts, ingesting the streaming data, building the APIs to deliver the stats, game day support, and even onboarding and supporting partners. This startup mentality, coupled with our partnership with AWS, has resulted in an insane number of stats amidst an explosion in growth and visibility. So I'll give you a crash course on how we collect the data, why we chose what we chose, and then we'll talk through a sample of stats to give you a teaser on the types of stats that we build on every single play. And then Elena will come back and walk us through how they built one of the first machine learning models that they built, the QB passing score, why that was such a difficult problem, why we thought that there was an opportunity for real innovation here, and how they delivered one of the most illuminating stats that we have today. And then RT will come back and show us just how impactful this partnership has been from the perspective of our business and media partners, our teams, and ultimately our fans worldwide. And then there will be a Q&A. So a little bit of background. In every year for the past 30 years, the #1 most watched show has been? Thank you, yes, yeah, Super Bowl. NFL games accounted for 82 of the top 100 broadcasts from last year. The average season averages over 16 million viewers per game. Now, this is more than the NBA Finals. For our fans, the sport's continued appeal might come from the chess-like combination of strategy, game preparation, and sheer athleticism that goes into every play. You may have heard that this is a game of inches. Everything matters in this game, from building the perfect roster to the field conditions at kickoff to making the perfect play call at the perfect time. In Super Bowl 52, the Eagles called the Philly Special. That was the only time the entire season that Doug Peterson made that play call. And if you remember, it resulted in a touchdown and ultimately an Eagles victory. Now, since the beginning, the NFL has been capturing a wide variety of stats. And these have been your typical box score style stats. Boolean expressions like, oh, was it a sack? Was it a catch? Or measurements based off of the outcome of the play, like, oh, that was a 6-yard gain. Or aggregations over the game or the season, so 7 receptions, 142 yards. We don't know how many yards after contact Walter Payton got. And we don't know how many low probability catches Jerry Rice caught. So the NFL realized that we needed a better way to capture player tracking data and try and make sense of the game. How do we quantify what football experts know intuitively? Such a system could reveal insights about game dynamics that would benefit fans and players. Insights such as, well, how does this quarterback perform against the man versus the zone? Or how did this one big play completely change the win probability in a team's favor? Matt Swenson, Senior VP of Product and Technology at the NFL, says this, machine learning is unlocking potential for us to do more than we otherwise could in a timely manner with a high degree of confidence. Said another way, we're capturing so much data now, and we wanted to find the best way to leverage it. With all the data that we're collecting, we can now effectively use machine learning to find what data points are relevant and what are not. So how do we capture this data? Well, today our tracking system uses RFID, or radio frequency identification. There are chips in all of the players' shoulder pads. They're in the ball. They're even on the objects on the field, like the pylons and the sticks. Every venue is outfitted with an array of sensors to collect the signal from those chips. And it sends us the location along with the speed and direction in which it moves. Now, why did we choose RFID? In 2013, the league sent out an RFP to capture the player tracking data. We evaluated a lot of technologies, and you might be wondering why we didn't go with another one. Optical tracking, which is used to great success in soccer and baseball, is unfortunately unable to distinguish players when they're in a scrum and a pileup. And that's a situation that happens quite frequently in football. Another technology, GPS, at least at the time, the accuracy was measured in feet. And again, this is a game of inches. So we decided on RFID, and we deployed the system in time for the 2015 season. We learned a lot in that first season from working with the game day operators, working with the players and the players' union, working with our media partners to make sure that we didn't conflict in our frequency band. So from all of those learnings, we typically consider 2016 to be the start of the NGS era. Now, looking at this bird's eye view of the field, you can think of it as a simple XY coordinate plane. You have 0, 0 on the bottom left, and then 120 on the x-axis. That's 100 yards for the field, plus 10 yards for each end zone, and then 53.3 on the y. The tracking system is capturing the signal from all of the chips on the field. It's triangulating its location and sending us this data 10 times a second. This data includes things like location, x, y, but speed, acceleration, directional and lateral load, even orientation and direction. Now, those you can think of, OK, if I'm a linebacker and I'm running full speed towards a quarterback, my orientation and direction of travel are going to be the same. Whereas if I'm a corner and I'm backpedaling and I'm covering a wide receiver, my orientation is facing one way while my direction of travel is facing the other. These data points form the building blocks for everything that we do on next-gen stats. And it represents a tremendous resource for the league's teams and media partners. So since 2017, AWS has been the official technology partner from every aspect of the development and deployment of next-gen stats. AWS stores this huge amount of data that's generated by the tracking system and all of our derived stats, which is over 300 million data points per season. And then my team, well, we use over 40 AWS services. Your usual suspects like EC2, VPC, Lambda, S3, but also Amazon SageMaker to quickly build, train, and deploy new models, or Amazon QuickSight to analyze and visualize this data. Now, every NFL broadcast that you see today will have real-time insights using next-gen stats powered by AWS. PRO304 built the NGS machine learning pipeline to quickly and easily deploy machine learning models capable of interpreting gameplay. And what PRO304 provided us, my team can then maintain, support, and iterate on. For example, when a season is over, we have a new season's worth of data that we can retrain the models on. Or we can take an existing model and see how similar it is to a different situation and come up with a completely new stat. Today, we have over 24 machine learning models running inference during the game, either on every play or even the real-time streaming data. Now, let's look at a couple of those. In this animation, you see a deep pass to Deebo Samuel. This has a completion probability of 27%. Now, what does that mean? Given roughly similar situations, the average quarterback is going to complete this 1 in 4 times. How do we come up with the completion probability? Well, we take all of the tracking data from ball snap to when the ball reaches the receiver's hands, not when he catches it, but when it reaches his hands, because that's the end of the quarterback's job. And we reduce all of that data down to 11 key features. Features like, how fast is the quarterback running when he releases the ball? How close is the receiver to the sideline? How far downfield did the ball have to travel? How close are the defenders to the receiver or the quarterback? Now, completion probability also gives us this. If a quarterback's completion rate is 75%, but the average of his probabilities was 67%, he's actually 8% over expected. And this is one facet of the individual quarterback's impact to his team. Now, the vast majority of machine learning being done in the cloud today is being done on AWS, which is why AWS is the perfect partner for the NFL to leverage the power of its data. Matt Swenson, Senior VP, says this: partnering with AWS meant that we didn't have to arm ourselves with a team of data scientists. We were able to get up and running quickly on the maintainable, iterable, and extendable solution from PRO304. Said another way, we didn't have to reinvent the wheel when we wanted to try something new. So the NFL is using the power of AWS ML, creating new stats, improving player health and safety, while delivering a better experience for fans and players, all in real time. Real time is never a non-trivial constraint. And so now, to show us exactly how PRO304 built the QB passing score, Elena Ehrlich. Elena.
Thank you, Andrew. And yes, these are exactly the kinds of considerations that we take into account when designing machine learning solutions. We don't only look at the immediate problem and its constraints, we also want to look ahead at reusability and generalizability constraints. So in this session, I'm going to walk us through exactly how we approach the modeling for the quarterback passing score. So let's zoom out a little bit and let's look at the business criteria that NFL really wanted to address. Now, when fans are evaluating a player's performance, what they're really doing is they're measuring that player's execution in a specific play against their innate sense of his potential. Now, preceding metrics did try to capture this. Madden, NFL passer rating, ESPN's total quarterback rating, Pro Football's focus grade, but these did draw criticisms from fans and from commentators alike. Actually, those kinds of feedbacks proved very useful to us because we used them to enumerate the kinds of intuitions that were being violated by those old metrics. And therefore, this became our business criteria. So let's walk through those. First of all, we want to have a quarterback passing score that can remain calibrated to the relevant data. Previous metrics had been calibrated to data that was deemed relevant in the 1960s, in the 1970s, but is obsolete in today's game of football. For example, the NFL, they've moved the kickoff line 3 times since that era. And the absence of that or other league changes in those metrics models have rendered them inaccurate. Secondly, we want to have a quarterback passing score that is correlated to winning. A quarterback is measured on how well he performs under pressure decision-making and then how well he executes those decisions with precision. So the better he is at that, we expect to have more points outcome and therefore more winning. Now, I don't expect the quarterback passing score to be perfectly correlated with winning because there are other factors, other players that are going to influence that outcome, but previous metrics were too uncorrelated to be accurate. Additionally, we also want whatever quarterback passing score metric we create, the formula, we want it to be robust against player anomalies. For those of you who remember, Kyler Murray, back in 2019, he won the Offensive Rookie of the Year award. Ironically, the same year that he received the low Madden score of 77. So we were determined to eliminate discrepancies like that. And lastly, we wanted to be able to design our metrics so that it can scale to different granularities, but with consistency. So what do I mean by that? I mean that I want to be able to score the quarterback across his whole season or even down to one specific play. A root problem with preceding metrics is that they weren't able to scale to different granularities, whether you want to just look at the play, look at the whole game, look at his performance across the week, across the season, or even other split-level contextualizations. Now, trying to encode those kinds of intuitions into a machine learning model actually proved quite non-trivial. Our science team worked very closely with the next-gen stats team. We worked to get it from a proof of concept to go live for season 2021, and then 3 months later to go public in time for Super Bowl 56. Now, the next-gen stats team, they were able to provide us with subject matter expertise on football, on their data, and on their downstream integration requirements. Conversely, what PRO304 really needed to deliver to them is we needed to be able to use the breadth and the granularity of AWS services so that we could tailor our solution to the customer's ideal of what's maintainable, extendable. This means that they can maximize their value proposition, but also so they can have lasting self-sufficiency after PRO304 exits the project. As Senior Director Michael Cheese said, NFL they have lean engineering teams, and they also have very tight deadlines. So what PRO304 really needs to be able to do is deliver, yes, impactful machine learning models, but that remain intuitive for their teams to own and expand and control. Now, for the next-gen stats team and for fans, it's very intuitive to measure, to grade how well a quarterback is performing. But our goal is to do that in a completely data-driven way that isolates the quarterback's contributions to the play separately from his teams. So what is the goal? We want to measure how well the quarterback performs given game clock and the pressure that he's under. Now, game clock and the pressure that he's under, these are measurable quantities. Game clock, this is a time measurement, and the pressure that he's under, well, this can be numerically represented from the time series that we're getting from the 22 players' RFID shoulder pads. In our case, creating a predicted distribution, sorry. No, actually what I want to say is, so those two inputs are measurable. But the output that we're looking for to mark that how well the quarterback plays, this is not something that's immediately measurable, right? Well, it's not a tangible, tractable metric in and of itself. So we needed to look at something else that can measure this. What we focused in on is the yards gained. So what we wanted to model is we want to be able to predict how well a league average quarterback could get the yards gained. And against that, we can compare it to the actual yards gained by that specific quarterback. In comparing this, if I can calibrate how well he got his actual yards gained against a league average quarterback's predictive yards gained, I can therefore quantify his relative over or underperformance. Now, in sports, the most exciting plays are the ones that have extreme outcomes, such as a breakaway speed or extreme yardage gain. Now, predicting and calibrating extreme outcomes is very difficult because extreme outcomes, by definition, are rare and they're infrequent, and we have very few examples from which to learn from them. In our case, trying to predict a distribution for the yards gained based on the 22 players non-stationary time series, this is going to require a lot of robustness, and we needed two types of robustness. One, we need to be robust against the prediction of yards gained that we want, but we also need to be robust in the percentage of probability of how likely the actual yards gained were that we observed. So for example, yes, I want to be able to predict 25 yards gained, but conversely, if I observe a 30 yards gained, I need to be able to quantify, was that 15% likely, so medium difficulty, or was that 3% likely, very difficult, i.e. an amazing accomplishment by that quarterback. Since I said that we want to take a completely data-driven approach, let's look at exactly what those data are. We're receiving updates every 100 milliseconds from those 22 players' RFID shoulder pads. So this means that we're getting position, speed, acceleration, the player's direction, and their orientation. That's 8 telemetries per player per time step. Now, the input sequence, the input time series sequence that we're going to extract from the RFID time series, this is actually a variable length. It's going to begin with the snap, and it's going to end when the quarterback releases the ball. So for example, a quarterback that takes 4 seconds to release the ball after the snap is going to result in a time series of 40 time steps. Or a quarterback that takes 2.5 seconds to release the ball after the snap is going to result in an input time series of 25 time steps. The table that we see over here, this represents how a play's data is going to look as a matrix. So what we see here is each row is going to correspond to a single time step of that play, with 8 telemetries per player times 22 players for 176 columns of that matrix. Now, what you'll also notice is that from going from left to right, we see the offensive team followed by the defensive team, where the players are ordered according to their ascending distance from the passer. So now, in order to collect the data from which we want to train the model on, we collected data from the preceding 3 seasons. This gave us approximately 50,000 plays. Now, 50,000 plays, this is a huge amount of data. This is approximately 34,000 completions, 15,000 incompletes, and about 1,200 interceptions. We definitely want to use all 50,000 plays to train our model. This is because we want to have maximum coverage and representation from any possible play outcome that can occur. And like we said, extreme plays don't have very many samples from which we can throw away. So to train 50,000 plays, 50,000 data, this is really high volume. So you can expect a model training time of around 8 to 10 hours. And actually, this is perfectly suitable because we train the model ahead of the season. So this is not a problem. A key constraint for us was that when we perform the inference call on the quarterback to get his score as soon as he's finished the play, we need that inference call to be returned to us in real time. So under 1/1000th of a second, or in other words, in time for the first replay. Okay, now in the previous slide, I showed you how one play is represented as one matrix or one table. Here, what I want to show you is how we fed 50,000 plays, so a huge amount of data, into our model architecture. You see here in the lower left, the 50,000 matrices are fed into a temporal convolution network, a TCN. This is the neural network that is best suited for learning the dynamic complexities across all the plays. It can handle plays of different durations, and it can also learn the long-term dependencies between sequential inputs. Now, plays also have static features, such as game clock, the current down, the number of games remaining this season, because these all affect other player strategies, it affects their decision-making, and it affects their performance under pressure. So what we do is we concatenate the vector of static features with the dynamic game state that has come out of the temporal convolution network, and that concatenated state we pass through the multi-layer perceptron for our network's final output. In our case, a probabilistic distribution of predictive yards gained. Now, the output of this network is really worth careful consideration. Naively, we could have just outputted a point estimate, like we predict 7 yards gained and actually it was 5. However, this would fail to achieve the desired outcome of measuring the play's outcome against its potential. And this brings me to my most critical point, which is that not all errors are created equal. So 2 yards gained under very easy circumstances is not the same as 2 yards gained in difficult circumstances. And yet they would both have a mean absolute error of 2 yards. So naturally, we want to go for a probabilistic distribution, or distributional forecast. So now we want to consider what kind of probability distribution best suits our problem. So we definitely know from our business case that we need a probability distribution that is flexible to all the play types. Let's have a look here at our data. So in the right graph, we see the empirical distribution of yards gained from interceptions. And we can see that whatever probability distribution we want for our model, we need to capture symmetry, since an interceptor can either be tackled at the 20 yards mark where he intercepted the ball, or he could run it back maybe negative 20 yards. Conversely, if we look at the blue distribution, which is the distribution of yards gained in completed passes, we see that our probability distribution for our model would also want to be able to capture asymmetry, since it's vastly more likely that the quarterback is going to throw in the positive yards gained direction of his end zone. There are even those plays for which we would want to capture bimodality. So imagine that the quarterback passes to the receiver who has one defender closing in on him. Now, the range of yards that's likely to be gained is either going to be the incremental 1 to 2 yards if he gets immediately tackled by that defender, or if he evades that one defender and makes a run, he'll have a high yardage gain. Either way, when we're looking at classical distributions like the gamma and the Gaussian that you see in black here, attempting to fit those two play types, we see that they are not flexible enough to handle all play types. And furthermore, classical distributions like those, they focus their accuracy on the center of distributions. And like we've already discussed, in sports, the most exciting outcomes are the ones that occur in the extreme outcome tails. So we really want to have a probability distribution that can accurately capture what's happening in the tails. For this, I'll redirect you to the right-hand side where you'll see the splice-bin Pareto model and its corresponding distribution. Now, the splice-bin Pareto model is something that AWS PRO304 invented to solve specifically this problem and therefore other heavy-tailed extreme outcome problems. Okay, so if we string together the data, the model architecture, and the splice-bin Pareto model, we now arrive at the solution that allows us to score the quarterback on his performance. Since the splice-bin Pareto model allows us to quantify how likely each incremental yard gained was, what this allows us to do is this allows us to take the actual yards gained by that specific quarterback and evaluate it in the cumulative distribution function of the predictive yards gained for a league average quarterback. So I'm taking the actual yards gained by the specific quarterback in the CDF of the league average quarterback's prediction, and I'm getting a ranking between 0 and 1, which that ranking is actually the quarterback passing score at the play level. So now, if we have the quarterback passing score at the play level, you can see that it's straightforward to aggregate across other plays. So for instance, we can aggregate across all the plays in that game, all the plays in his week, all the plays in the season, or other split-level contextualizations. Like what we see over here in the upper right-hand corner, we see Geno Smith, when we're aggregating his score across all deep passes, he scores a 99, which makes him the highest ranked quarterback for deep passing. Or what we see here in the lower right hand is we see quarterbacks listed according to their score for passing EPA, expected points added. One of the business criteria I mentioned is that we want to make sure that our quarterback passing score correlates well to winning. What you see here on the left-hand side is, let's look down at the bottom, we see when the quarterback passing score is low, like in the red 60s, we see that it corresponds to a very low win probability, the red 10%. But as the quarterback passing score increases, let's say to the blue 90s, we see that correspondingly, the win percentage increases to like the green 66. And that corresponds to an 80% chance of making the playoffs. What we also want to see is, does our new quarterback passing metric correlate well to winning better than the preceding metrics correlated? And what we see over here on the right-hand side is, yes, it does. So the Next-Gen Stats team, they created and deployed these models in Amazon SageMaker. What PRO304 did is we delivered a containerized model that was seamless to deploy in the EKS cluster. This meant that there is full control over resource allocation, the response times, and the reliability. So what PRO304 did is we do the heavy lifting, we do the model development, the analysis, and the productionalization, and Next-Gen Stats has full control over when to call the model API, where to store the outputs, and how best to serve our partners. This actually allows us to have real-time insights during the NFL game. So when the data streams in from the stadium, so it streams in from the stadium, and now it's inside the AWS environment. Once it's inside the AWS environment, it undergoes 100 processes in under a second. So through that whole pipeline in under a second. And this results in the NFL being able to produce APIs. They're able to create on-screen graphics. They're able to supply sports announcers with more unique data points about which to talk. And this allowed them to expand their media team and tools. If you want to see this firsthand, you can use this QR code to redirect you to demo code that shows the splice-bin Pareto model fully pipelined. However, I'd like to invite my colleague Artisani back on stage to enumerate the kinds of business outcomes that NFL was able to achieve from fan-engaging metrics such as this one.
Thank you, Elena. Let's first talk about some of the rising winds the NFL NGS has experienced over the recent years. Next-Gen Stats has now over 242,000 followers on X, formerly known as Twitter. What started as just one broadcast partner in 2017 is now all 5 broadcast partners in 2023 for all the games, including non-A games. The number of NGS segments has increased from 1 or 2 in a single primetime game to 3+ in every NFL game. Next, let's talk about the resulting Next-Gen Stats and what they mean for the NFL. Among a number of next-gen stats that we helped NFL develop, let's start with passing score. As Elena just shared, this is first of its kind of AI tool that combines 7 machine learning models, including a new one, to predict the value of a pass before the ball is thrown, to evaluate quarterbacks' passing performance. Additionally, one of the key aspects of the PRO304 engagement model is to enable the customer teams such that they can take some of this work themselves and become independent. And this also helps them become comfortable in maintaining this work in the long run, which is, say, machine learning models in this case. Mike Band, senior manager of NFL NGS team, stated, "The intricacies of this battle over ball control and field positions is hidden from advanced analysis. Yet, punt and kickoff makes roughly 1/5 of the game and can have a major impact on the field position and game flow." To address this gap, the NGS team developed expected return yards, the first ever advanced set of models that focus on punt and kickoff returns. It's 4th down and inches. The clock is ticking. The pressure is mounting. The decisions have to be made in a split second. Does the coach play it safe and kick it, or risk it and go for it? Coaches relied on their experience and gut instincts in the moment to make those decisions. However, we have helped NFL develop these stats that can help coaches make more informed decisions. Additionally, fans can know what the optimal call is based on the numbers. The 4th down decision guide answers the question, what is the win probability of a team if they go for it, attempt a field goal, or punt? This is an AI tool to evaluate 4th down and 2-point conversion decisions. And being right in those situations can spell the difference between winning or losing. And our model shows teams are increasingly making the right call. In other words, when the number says go, teams are increasingly going for it. And when the number says punt or kick, teams have typically gotten it right there too. As you can see on the chart on the right, Coach Stefanski, Cleveland Browns head coach, certainly optimized those decisions by making the right call when the number said to go for it 38 out of 48 times, which is 79%. Not all passes are created equal. Yet, quarterbacks get the same credit of completion whether the pass travels 60 yards downfield to a receiver in a double coverage or pass travel 2 yards behind the line of scrimmage to an open running back in the flat. In a complex environment like the game of football, these traditional box score stats, such as rushing yards and yards per carry, they do not provide the complete context to reliably quantify teams and players' rushing performance. These stats only provide a partial picture when the rush was attempted. The ball was carried by a certain number of yards, without telling you how and why the ball carrier succeeded or failed. Our completion probability model delivers that added context to each passing play. Have you ever wondered how many yards a ball carrier will gain after a handoff? Expected rushing yards model can help estimate that. This model produces the full probability distribution of outcomes in terms of yards gained, which also derives the likelihood of a ball carrier gaining a first down or scoring a touchdown. The neural network modeling architecture built for handoff was replicated and trained on the quarterback run plays using Amazon SageMaker, a new quarterback dropback classification model. For a play with a handoff, the relative speed, direction, location of all 22 players is taken at the moment of handoff. And for plays without a handoff, the model uses a snapshot as soon as the quarterback makes clear his intentions to run. As it becomes more common for the quarterbacks to make plays with their legs, fans can now quantify the impacts of these quarterbacks' runs have on the game. And lastly, expected rushing yards is the foundation model the NGS team used to build those additional two models, expected punt and kickoff returns. The design of an offensive play is predicated on the immediate movement of the quarterback. Does the signal caller take a straight drop? Does he roll out of the pocket? Is he forced to scramble? Is it a designed run? Next-gen NFL team designed this model to classify quarterback dropback types based on real data using the player tracking data. By diving deeper into the splits and using this new quarterback logic, NFL can now more accurately classify a play call's intended play type. A play where the quarterback drops back to pass, scrambles, and run can now be credited as a called pass play. This distinction allows for more robust analysis of run-pass play calling tendencies. The top plays of the NFL game, week, or season are the plays worth watching again and again. By combining several different NGS models, Next-Gen Stats Big Play Score grades every play from score of 0 to 100 based on three primary components: win probability effect, expected points added, and play improbability. Win probability effect is derived from win probability model. Expected points added comes from expected points model. And play improbability factor is a play type specific complex combination of completion probability, expected rushing yards, and expected receiving yards. Modern fandom can be driven through one's fantasy team as much through allegiance to one's favorite football team. As such, Next-Gen Stats team has been focusing on fantasy football to deliver the actionable insights and metrics for fans to win their leagues, and for some leagues, avoid that dreaded last place punishment. In fantasy football, opportunity is the king. Historical snap counts, touches, and targets are considered as proxies for the player's involvement in an offense. More volume equals more fantasy points, according to many fantasy football fans. But not all opportunities carry the same weight, according to many fantasy football scoring formats. A carry at a midfield yields much less value than a rush attempt from an opponent's goal line. Expected fantasy points and derivative stats, such as fantasy points over expected, are the two metrics fans use to make in-season adjustments. Expected fantasy points strips away players' talent and efficiency and focuses solely on the opportunity. Have you ever wondered how the play would have evolved if the quarterback had targeted a different receiver? Would the defensive backs have reached the receiver in time to stop the big gain? Defender ghosting model can help estimate that. This model predicts the trajectories of the defensive backs after the ball leaves the quarterback's hand. Thus, it can help evaluate quarterback's decision-making. To summarize, in this session, we shared how AWS PRO304 and the NFL Next-Gen Stats team have been leveraging cutting-edge technologies such as machine learning to build these stats from ground up or retrain existing ones. We also shared how these stats have helped transform the NFL business by increasing fan engagement. Mike Band of NFL team stated, "There are so many games within game. There are so many insights to find, and there are so many stories to be told." PRO304 continues to help NFL transform their business by building more stats and telling more stories. If you would like help in defining strategy to transform your business through innovative technologies such as Gen AI, AI/ML, data analytics, and others, need help with execution, please reach out to PRO304 through your account team or through this request form. And lastly, your opinion matters greatly to me, Elena, and Andrew. So please take a moment to complete the short survey in your mobile app so we can continue to deliver the content you need to be successful. And with that, we will now open for Q&A. And I would like to have Andrew and Elena join me here. Thank you.
Is the NFL using this data to enhance player safety as well when it comes to the impacts? Because these are big people running at very fast speeds to try to help with concussions and those kinds of things as well?
Yes. And the direct result of that was the change in the kickoff rule to not have the running start. But they basically used our data to kind of help justify making that rule change. So we do have a player health and safety team kind of using the data for that purpose.
A common kind of rebuke when fans are talking about a quarterback's performance after the game is, well, he put up all of these stats in garbage time. Do your models account for maybe the quarterback's ability to deliver when it mattered versus when the game was really kind of out of reach? Or do you just sort of let it work itself out in this correlation with winning probability?
Oh, sorry, can I just say the question back because I didn't hear all of it? You're asking if the model is able to include other conditions that would help us deem whether this is a really critical play, important, and then because that pressures him more, he might be more nervous and that affects his performance. Was that the question?
Yeah, mostly. I'm sorry, I didn't realize. If a quarterback puts up a touchdown and 80 yards or something in the last 5 minutes of a game when he's down 20 points, it may inflate his stat line and maybe his performance looks better on paper. But does your model say, well, it really didn't matter at the end of the day? He didn't do it when he needed to.
Yeah, I can answer this. So our model would capture that, not directly. So we don't have a feature in there that says like, does this play matter? Does it not? Or we don't have. That would be a binary feature. We also don't even have one that's on the spectrum. Like these are in the upper quantile of important plays, and these are not. So we don't have a feature directly like that. But when I mentioned that the plays do have static features. So the way you introduced the question, how you qualified it by saying what the exact situation was, and okay, it doesn't matter in that case because it's 5 minutes to the end and they're already winning, so it's not so important that he performs well right then. We did include those static features, so those would let the model know that if we're going to compare it to how well other players, so that will let the model know that these are the conditions, and then we know that those conditions make it not so important a play. And then there's going to be other plays like that where we see how other quarterbacks performed. So generally speaking, then they won't put so much effort in doing it, whereas if it's a really important play, all the quarterbacks will try to be executing very well, and then if that specific quarterback that we're looking at surpasses their average performance, then we know that he's able to perform very well in important plays, like under pressure. If this was your question, sorry.
I have a question about the RFID units. You mentioned they're in the shoulder pads. Are they at all noticeable, burdensome? How did you integrate it into the very small?
They're really small. They're about the size of a dime, maybe like 3 dimes thick, and they're placed in the epaulets of the shoulder pads, and so they're actually underneath the flap, so the players don't notice them. And because they're so small, they're also able to be installed in the ball as well. So,
Okay,
yeah,
great.
they do, sometimes they can fall out, and so thank God we have two. We're able to, disregard one of the tags if it's just like lying on the field somewhere, and then just focus on the one tag. But yeah, they're really small.
Two quick follow-ups. What type of manpower do you have, monitoring the RFID units like that? Like if one falls out during the game, is that a big, lift in terms of people monitoring?
Well, yeah, I mean, we're monitoring every single game.
Yeah.
We've got crews at every single stadium, and they're responsible for like activating the chips and making sure that the chips are assigned to the right player. Sometimes like players will change their shoulder pads and we'll have to scramble to try and get emergency tags on them. And so we have a really good relationship with all of the team's equipment managers. And so they're monitoring all of the data as it's coming in. And then almost immediately, once we realize that, like how a dropped chip will manifest itself is like just very erratic tracking behavior. And so we're able to discover that really quickly, find the exact point where the erratic tracking began, and then retrack the data from that point. So we'll have clean data throughout the entire game. So.
Yeah, and I think you addressed it a little bit there, but just was wondering like how hard it is to coordinate everything with all the different people, like the event. Was that a process or was that pretty easy?
Oh, it's a huge process. I mean, everybody's really lean. There's one game day coordinator at the stadium, and he's responsible for coordinating all the frequencies that all the media partners have at the stadium. So getting his attention and just working with. So another indicator is the crew that's there to operate the tracking system. They're there 6 hours before the game to make sure that this is all going smoothly. So it's a lot of work to do leading up until kickoff. And then we've got crews who are remote, in the Knox, and then we're also monitoring. Like my team are also monitoring the games as they come in too. So.
Do you ever see this data being used to help the referees, like calling a false start or like those faults?
No. But we do.
Have the data.
Not false start, but we have used. We are now using the data to kind of track where the ball goes out of bounds on kick plays. And so, if it's like super far out of bounds and the ref is 5 yards off, we know exactly where it goes out. And so there's a signal that gets sent, and then the football ops people will see that note, be like, oh, actually the ball has to be placed on the 16-yard line. And so they get that information within a couple seconds of the ball going out of bounds. And so we're able to get that, in time for the next play.
So for the paper that you guys produced, I'm actually curious, so with the streaming peaks over threshold methodology, I'm curious, when you guys look at how to learn the tail quantile, what are some of the new methodologies that you're using to make sure that you can reduce domain knowledge dependency? Are you looking at maybe generative approaches, or what are some of the new techniques that you might be looking into?
Sorry, can I again say the question back to you just to make sure I capture it?
Yeah.
You're asking, so for the distribution,
Yep.
that we said that we want to make sure we focus very well on the tail, well, not just only on the tails, but equally on the tails as
Yep.
the base. You're wondering how we did it and how our method would compare to other potential methods out now.
I'm actually just interested in some of the newer approaches that you're looking at to make sure that there's less dependency on the tau parameter being calculated
Oh.
right? Yeah. From the paper, yeah.
Okay.
Yeah.
So, sorry, I'll just say it so that other people can understand. What he's asking is, it's actually a very good question because it's still an open research problem. So yeah, let's say the way I presented it might imply that we know exactly where the tail of a distribution begins, but this is not the case, right? If we knew exactly where the tail begins, this is already a huge leg up on the problem. So yeah, once you know where the tail begins, okay, you can try to fit how heavy it is, how light it is, or maybe if it's even a finite tail. But yeah, that's only once you know, and what he's calling TOF is the threshold where we now say, before this TOF, it's part of the middle distribution, and after this TOF, it's considered the tail. And so, for our paper, no, I would say this, no, for our paper, we didn't look into a way that does it very robustly. But we did do it in such a way that doesn't depend on the domain. So the way that most applications will do this is like, you know your industry very well. So if, let's say, you need to predict how high rivers are going, and that's important because once it floods, you can't take your cargo ships down and all your suppliers are stuck, right? So what we did instead is, like, even though we fixed it saying that we're going to say that the TOF is going to begin at the 5th, and for the lower tail, the 5th percentile, and at the upper tail, the 95th percentile. Actually, this gives us a dynamic TOF because the quantile is fixed, but every time we update it with as the streaming data comes in and we update the distribution, where the 5th quantile and the 95th quantile land, this actually moves. So there is some inherent capture that's not based on the domain, but it does provide a time varying threshold. Yeah.
Thank you. I guess it's a sort of similar question to the kickoff return out of bounds point you made earlier. Is it today, or do you possibly foresee it being used in the future to help officials make decisions about whether or not a field goal or an extra point actually went sort of between the uprights or not? I'm thinking about situations, with sort of the famous ones that we've all seen of where it's slightly over the height of where a goalpost is.
Right. I mean, that doesn't happen very often because those goalposts are pretty tall. But yeah, I've seen that, and unfortunately, the accuracy isn't so much that we can get it like to within an inch, right? So because we know that the accuracy is only so much, we're not going to make decisions on the game outcome based off of that.
So we are almost at time. We have time for maybe one more question.
Okay, I may just have 2 points. So for the SPP, the spline, the bin, Pareto model that you mentioned, that's the distribution of the yards passed, right? So basically, your upper bound is 100 yards. Does that help you constrain the problem? And second question, when you did this model training, is there anything counterintuitive, such as a single factor or combination of factors that you found that counterintuitively contribute to the success of a team or quarterback or skills player, et cetera?
Okay. So sorry, for the first part, so the when we are talking about the splice bin Pareto distribution, it can be for anything. It's not just for this problem, but in this problem, so you're saying because the field we know it's 100 yards, that's like an upper bound on how far it matters that the quarterback threw the ball. Even if he overthrows it, it's like you're going to cap it at 100 yards. This was the question. So if he throws it from wherever the line of scrimmage is through to the end of the field, then that greatly reduces the problem that you don't need to have so elaborate a model. But since this is not like what's always happening, you need to have a model that can account for when this doesn't happen, right? And usually this doesn't happen. So in that case, actually, so you don't know. So you know how when the other gentleman asked the question about where the tail is going to begin, given a certain play type, so given like maybe this play is very hard, then the quarterbacks might not throw so far, but then if one does manage to throw a little bit farther, you want to be able to get those tails, and you'll only have a few data points from the preceding 3 seasons where some quarterbacks were able to do that. So actually, even though you have your bin distributions, actually we did do 100 bins, one for every yard of the field, to be comprehensive. But then with what that gentleman asked, when we are looking at the 95 percentile for that specific play type or similar play types, you'll notice that 95% threshold cuts off really early. So those rest of the bins don't matter, and then you end up fitting the tail for what is ever suitable for the tail for those types of plays. Does that make sense? Yes. And I don't remember your second part of your question.
The second question is whether there's any factors or combination of factors.
Oh, that were counterintuitive? I will just need a few more minutes, and we can discuss it afterwards. I'll just need to recall it because, in hindsight, when I think about the problem, I just remember how things worked out well, and I'll just need to have like a minute to remember when I was doing it, maybe I thought something for sure was going to work, and then I was probably embarrassed in front of Andrew when it didn't, and I had to revise it. So no, I'll definitely jog my memory.
Just wondering if there's any money ball moments. That's all.
Oh no, then I'm not sharing that.
So we are at time now. I think we'll end the session now, but we'll all wait outside there in case you have any additional questions. Thank you so much for attending the session today. Hope this was helpful, and have a great rest of reInvent. Thank you.